Good morning, my name is Sgadari and in this video I'm going to present my master thesis. The problem consists of a nonlinear system S having an input U and a measured output Y. We apply to the system a properly designed input signal and we measure the corresponding output. From this data, our goal is to build a mathematical model of the system. To do so, we assume that there exists a model family M such that it includes system S. Inside of a model family there are several model classes, each defined by a specific set of hyperparameters eta. First task is to define the optimal model class containing system S. Any model class contains several models, each determined by a specific set of parameters theta. Second task is to define the model in optimal class that coincides with target system S. For this scope, we proposed an iterative procedure where, given a model family M, we select a model class and then we find the optimal model in the class. If it is close enough to S, we stop. Otherwise, we update the class and repeat the procedure. But let's now focus on optimal parameter selection procedure. We first take into account our input-output dataset and we focus the most on the output. Now, we consider as given a fixed model class with output error. This method is based on set membership identification, whose main assumption is that additive noise on the output is bounded by a certain value W bar. This allows us to define the tube of all possible outputs between Y at time k plus minus W bar. We can also define the set of class parameters compatible with input-output and noise bound, the feasible parameter set. Then, we sample the feasible parameter set, assuming a certain probability distribution. After drawing a sufficient number of samples, for all of them we simulate the corresponding model's output. We then compute for each simulated output the cumulative sum of the distances between the simulation and the tube for all time instants. And finally, we select as optimal parameters the one providing the minimum value of this distance. To determine the model class, we use a growing and pruning process. Growing adds features, increasing flexibility. Pruning removes less relevant features. This iterates until we identify the optimal model class. In conclusion, the algorithm was implemented for two significant model families, each with distinct challenges. It was tested on both simulated and real-world case studies, showing promising results.